So the title of my talk is High Resolution BGA Inspection in 2D and 3D with stereo line scan cameras. Yeah, few lines about myself. My name is Timo. I'm leading a team within ChromaSense that is called Research and Innovation, and this is part of the R&D division. ChromaSense, for those that don't know us, is a manufacturer of machine vision components and machine vision solutions. And we specifically focus on line scan imaging and line scan imaging applications. So the outline of this talk is I'm going to introduce in one slide what are the challenges with BGA inspection, and then move to a brief overview on, let's say, inspection technology that is typically used for BGAs. This is not exhaustive, but it should give you a rough feeling on that. And then we'll move to line scan imaging and specifically to technology that ChromaSense developed for BGA inspection. I will conclude this talk with a short summary at the end. So BGA stands for ball grid arrays. And well, for those who don't know, a ball grid array is a type of surface mount chip carrier for integrated circuits. And I think most easy to understand what BGAs are and what they are used for is like with a plot like the one, this schematic view on the right side. This is a typical system on chip sandwich, let's say. So we have a PCB board. Let me see if I can get here a laser pointer. A PCB board, and then we have a processor board on top of it, and for instance, a memory board. And the BGA is essentially this carrier for the memory or the processor logic here. And the balls are the connectors for interconnecting, for instance, the memory lanes with the processor and other hardware that is on the PCB. So why is it so challenging to apply inspection on BGAs? Well, a simple reason is that as soon as you stack those chips, you're not able to visually see them anymore. If you want to do 100% inspection on your products, which is typically required if you want to have a high production yield, you will have to inspect your parts before you actually assemble them. Well, once they are assembled, you cannot inspect them anymore in an easy way, let's say. Another challenge is that you have a high requirement on the accuracy and on the speed. 100% inspection means you want to inspect every single chip and every single ball on each individual chip, and there are hundreds of them. Yeah, so in order to achieve high speed, if you look into the manufacturing process, typically BGAs are manufactured or transported through the machinery in these JEDEC trays. So JEDEC is a standardized format for those trays, which can carry those chips. And in the ideal case, the inspection system can actually inspect the BGAs within those trays. This is a convenient way of having a fast way of inspecting them. What is being inspected? Well, there is a very long list, and I only mention a few tasks here. Tasks could be measuring the ball size of the ball grid array, the grid alignment, coplanarity of the balls within the grid. And there's a lot of inspection tasks that are related to the surrounding of the BGA. So meaning the substrate, contaminations, scratches, missing solder parts, and so on. It's a long list. And the criteria are actually 2D and 3D features. So I think you all know the 2D part of that. This is why I'm focusing here more on the 3D part of the inspection. And here is a, let's say, different technologies that are typically used for this. Based on triangulation principle is laser line scan. The idea here is that a laser line is projected on the object is moved, and an area camera observes the deformation of the laser line due to the surface height structure. There are various vendors for components that apply this principle. I named some of them. There are 3 points here indicating that there's actually many more. Yeah, another technology is structured light. It also fits quite well to BGA inspection because you can achieve quite high or quite accurate measurements. The principle here is you have a projector that projects different light patterns subsequently, and an area sensor that then acquires images. And from those different images, one can reconstruct the 3D profile of the object. Yeah, obviously, projecting black and white patterns means that the image acquisition is then void of color. So you can get a height profile here, but you would have to acquire an additional image to have an RGB representation of your scene. For laser line scan, a small drawback in that sense is also that it acquires a high profile image, but not a color image itself. Okay, another technological approach is color confocal imaging, which I know that it's used for BGA inspection. And you might know the principle here from microscopy. The approach in microscopy itself is very, very accurate. The principle is to detect light colors, which are then related to the object height. A drawback for BGA inspection I see in this approach is that it's in the microscope way how it's normally used. It's rather slow and a limited field of view. But there is one vendor that applied this principle to a line scan approach, so a scanning-based approach, which then can be realized in a much faster fashion. Yeah, the last technological approach that I'm showing here is stereo imaging. And stereo imaging works by having either a line scan camera or area cameras. You typically need 2 of them. And these 2 cameras need to observe the object from different perspectives. So different perspective views, similar like our eyes are working. Based on the difference between corresponding points in an image, one can reconstruct the height information. And one thing to mention here is that most vendors sell the components for a stereo imaging system, but you might have to calibrate it within your application. With ChromaSense 3D line scan cameras, this is different. We pre-calibrate them in our facilities, and therefore, in the end, when you buy this kind of line scan camera, you have a measurement system that is ready for absolute measurements. Okay, we will dive a little bit deeper into the line scan imaging approach. Yeah, the principle was just mentioned. You have essentially 2 cameras. In this case, they are in one housing. And in the special case of ChromaSense, I think we are the only ones who do line scan cameras based on the stereo principle for 3D measurement. We have RGB sensors, and those RGB sensors, they acquire 2 images with slightly different perspective. This is what is indicated in here. It's line scan, so it means the object or the camera needs to move relatively to each other. And we use high intensity line lights in order to achieve very fast scanning times. We have developed an API that is used for reconstructing the 3D scene, and essentially it does there's a pattern matching algorithm used for finding correspondence in the images. So what is quite cool in this system is that as an output, you have an RGB image, and this RGB image is actually free of distortion. This is part of our 3D calibration. And at the same time, you have the height information. So it's very, very versatile in terms of the data that you can acquire. And this can be even taken to the next level in terms of the possibilities that you have with line scan imagers for lighting. So you know also from area systems, different geometries can be realized. The same is valid for line scan. ChromaSense developed a large range of products like dark field illumination, bright field illumination, tube light. This is a kind of cloudy day diffuse lighting, or backlights. We develop them with different LED types, so you have a wide spectral range depending on the application you can choose. And what is pretty unique if you combine our cameras with our light sources is that you can do some kind of multiplexed image acquisition, which means that in one scan, you can acquire multiple lighting geometries. So an image that is acquired in bright field condition and an image that is acquired with the cloudy day illumination at the same time in a multiplexed fashion. Or you can acquire with multiple colors in one scan. And I would like to illustrate this in a bit more detail because this is very much related to what we do with BGA inspection. So for BGA inspection, we have developed a 3D camera. It's called 3D Pixar with a lateral resolution of 10 micrometer. This is what we understand is for the moment required for BGA inspection. It has a height resolution of 1 micrometer or a little bit more than that actually. 150 millimeters field of view. This corresponds to what you need to scan one entire JEDEC tray. And a speed of 184 millimeters per second. So really, really fast, probably faster than what is needed for the BGA production at the moment. So we also developed a specific multi-geometry, multi-color line light. And this is pretty unique. So I mentioned before that we have an RGB camera here. And the RGB camera allows us to encode in each color channel a specific lighting geometry. And in this case, we have implemented it in such a way that we have this cloudy day illumination indicated here in red with red LEDs. We have a dark field condition, a very flat angle light with green LEDs. And we have this bright field illumination implemented by blue LEDs. And the trick here is that due to the spectral separation, we can acquire all 3 lighting conditions in one scan. And the way how this looks if you acquire an image is like this here. This is a small part of a scanned image. And if you look at it like that, it doesn't make a lot of sense. But if you separate the color channels and you interpret them as let's say grayscale images, it becomes much more clear what is the idea here. So if we look at the blue channel, this is the geometry that corresponds to bright field condition. We can see very well the substrate, and we have a very good texture on the substrate. And this good texture is needed for 3D reconstruction. I will jump down. If we take the red channel, this is the tube light. It is very homogeneous lighting from from a wide angle range. And this is the preferred setting for 3D reconstruction of the ball shape. Okay, but if you look at the texture here, it's black. Essentially, with a tube light, you cannot see the substrate. So only by combining those two, you can actually get a good height image of balls and substrate at the same time. So the third channel is the green channel. It's dark field condition. And dark field condition is often used to detect contaminations on the surface, such as, for instance, dust. Dust becomes visible as bright spots. You can see them here on some parts of the substrate. So we have been doing a feasibility study to analyze how effective we can use our components for BGA inspection. And what we did is we scanned an entire tray of BGAs, like this JEDEC tray, and we used MVTech's image processing library Halcon for doing a defect inspection task here. I will not go into all details of the inspection. I think we don't have time for that. But just roughly speaking, we had to find each individual BGA, and then we had to find each individual ball in an automated fashion, of course. And then we could derive from that ball size, grid alignment, ball diameters, and so on. Also, we could derive from the height information, the ball height and the coplanarity, and also analyze the flatness of the substrate, for instance. We also use the images to find scratches and contaminations. This is something that you do from with the RGB images, or with a intensity image, and not from the height image, of course. The tests we did, they revealed that the scanning time for a whole JEDEC tray is less than 2 seconds, which is really, really fast. Essentially, that means 80 full BGAs per second, which corresponds to, in our case, for this example, something like, I don't know, 17,000, more than 15,000 balls per second. And each of them was individually analyzed. So, yeah, I would like to summarize what I have just presented. So the challenges with BGA inspection are that the inline inspection requires a high speed and a high accuracy. And line scan 3D imaging allows to combine both. So we have this very large field of view that allows you to scan an entire JEDEC tray and not only an individual BGA in a very fast time. Another really interesting property and a big advantage that I see from this technology is the that you only need one scan and you get 3D data and 2D data in different lighting geometries. So the line light multicolor, multi-geometry that we developed for BGA inspection is a perfect match here. The last part is just about the camera. The 10 micrometers 3D Pixar is exactly what is needed for BGA inspection. And the accuracy that we could measure with our feasibility study, which is for height measurements in the range of less than 1 micrometer, is exactly what is needed there. So I know this was only a very brief overview. The time that I have does not allow much more, but I invite you to send me questions offline, check our webpage, or find another way to consult us if you need more information. Thank you very much.
Thank you. And there are a lot of questions coming. So the first questions, 1 micrometer height resolution is very impressive. How do you manage precise object motion?
Well, this is a good point. In the end, you need a very precise linear stage to traverse the JEDEC tray under your camera. But this is not really rocket science. So we use standard linear stages, and they have an accuracy that is good enough for that. But yeah, I have to mention here, if the transport of the JEDEC tray is not accurate, our camera will not be accurate either, or will not produce, let's say, adequate results. So in line scan imaging, you always have to have the right transport, and this is something that can be just simply bought.
Mm-hmm. Next questions. What are the advantages and drawbacks of your technology compared to the color confocal technique from focal spec, for example?
So yeah, an advantage that I see is the ability to acquire your scene under different lighting geometries. We really see that this brings a big benefit for the versatile inspection applications that are given with ball grid array inspection. I don't think that this can be done with color confocal microscopy or the line scanning approach. And the other advantage that I see is that we have here a very wide field of view, and I am not sure if the focal spec products are actually capable of measuring in that high accuracy the same wide field of view of a whole JEDEC tray in one run.
Thanks. I think we have time for 1 or 2 questions, so please use the Q&A section. And the next question is, could you improve the depth accuracy by using a monochrome sensor? And if so, how much %?
No, I don't think that we can improve it by that. So the height resolution of a stereo camera essentially can be tuned by the distance of the 2 cameras. This is a property called baseline, and this is directly linked to the height accuracy. So in our case, I do not actually see a limitation by using a RGB sensor here. And maybe there is one thing I should add. This RGB sensor is not a Bayer pattern type. So actually it's a 3-line sensor, a 3-linear sensor. So we have a full line of red, a full line of green, and a full line of blue pixels. There's no interpolation happening.
Is there a solution available without using GPUs for 3D reconstruction?
Yes, actually we are developing at the moment, or we are looking into approaches of porting, let's say, the computational demanding processing on FPGAs. So for particular application, it makes sense to actually not use the GPU, but to do the processing on FPGA. And this will be something available for general public in the future.
Thanks a lot, Timo. How to overcome glossy surface when doing height measurements? Do you have an answer to that question?
Yeah, sure. So in our case, glossy surfaces are always a problem if the glossy spots become saturated image pixels, let's say. And the way how we answer that is by using lighting geometry or adjusting the lighting in such a way that we can avoid actually specularities. And one approach that can be done, which is maybe not related to selecting a proper lighting geometry, is to acquire multiple shots in different exposure times, for instance, and then do these conventional HDR imaging approaches for fusing the image data. But I have to say here, we are investigating doing that as a processing step in our cameras on FPGA, but this is currently not implemented. So currently, if we apply that in applications, then we do it as a post-processing step.
Thanks. Timo, you just show us the BGA inspection application. Are there any other applications which you can solve with your system? Yeah,
in fact, the 3D Pixar technology, so stereo line scan imaging, as a technological approach is very well scalable. In the end, it only depends on the type of lenses you use and, let's say, the type of distance of the 2 cameras relative to each other to adjust resolution, height resolution, and lateral resolution parameters. And therefore, the technology is very well suited. And if you look in our product portfolio, you will see that we actually go from this microscopic range of 5 micrometer lateral up to a macroscopic range of, I don't know, maybe 200 micrometers per pixel in lateral resolution. So applications really, I don't know, it's really the whole field of industrial application. And also outside of the industrial range, things like, for instance, inspecting roads or inspecting trains when driving, or driving trains, let's say, like that, or stuff like this.